Hi everybody, hope you're doing fine. I will talk about the differential operators, which I mentioned previously as matrices in some limit. So I'll discuss it briefly just to show you that differential operators are some kind of limit of matrices. So suppose that you have a first order derivative with respect to some variable of x of some function psi of x. All right. This is in quantum mechanics. You can think about psi of x is equal to a ket vector projected onto the position basis. Say it's position for the sake of simplicity here. So we know it is the limit when delta of x goes to 0 for this ratio. It is the function evaluated at some place after minus the function evaluated at the exact position. In the limit, when delta x goes to 0, you have the derivative. So it's for a given function. You have a function here. If you want to calculate the derivative, say here, and this is the position of. Let me put the graph this way. You can calculate the derivative, say here. Then you pick the function here and some place x plus delta of x, and this is the second curve, but in the limit it becomes the tangent here. You push one point onto the other until they are very close. In the limit, delta of x goes to 0 and you find out the derivative. But now look at the expression here. So a given function, I must remember that lines can be discretized. So we have a delta of x. This is the line of x, x1, x2, and all that. And you can write a vector in the basis of position. This vector corresponds to psi1, this is value here. Psi2 is value, it's the value of the function here. Psi3, it's the function at the third point here, and goes to the end point. So this x van, say here is some x of j corresponding to each one of these points. There is a vector in Hilbert space satisfying all the basis requirements. It's orthogonal, it's complete, and all that which is required for a Hilbert space. So notice the following. For 2 points here, say this is xj and this is xj plus 1. So here I can assign the value of the function x plus a delta of x, xj, for the sake of the moment. This is the interval, and this is the function evaluated. This function evaluated at that point xj. The derivative at that point, ddx of the function x of xj, psi of xj, say, is just psi of xj plus delta of x minus psi evaluated at xj, and all the things divided by the delta x. Now I am removing the, for the moment, I am removing the need of a limit, and I will call this delta of psi divided by delta of x. All right, so that's it. Now, if I want to evaluate a vector of derivatives, I can calculate the derivative at the point 1, point 2, all that, till I find the final point. Take for simplicity that the point outside the domain is just 0, and therefore, at the end, point previous to that one and after this one will go to 0. So I want to evaluate this thing here, the vector corresponding to all the derivatives of the function. All right. So what I need to do, look at in this case, I need to have corresponding to d of dx some matrix, which I don't know what is right now. I don't know what is this matrix right now. But when applying this matrix, the set of values in the basis of the, say, the coordinates here, will give me the derivative at some proper limit procedure. But if you say, if you use the following notation, psi of xj plus delta of x corresponds to the psi j plus 1, and psi of xj is equal to psi of j. The derivative at this point, at this particular point, I need to pick the next point, the next value of the function in the next point, subtract from the previous one, and divide it by delta of x. And for each j, I need to repeat this kind of calculation. This is some kind of computation of the derivative, all right? So it's a computation of the derivative. This way, notice that in the vector corresponding to the state vector psi 1, psi 2, I'll look exactly at the psi j plus 1 to calculate, and here I have the psi j minus 1 and all that. I want to calculate the derivative at this point. So I will have a matrix here, right, which corresponds to the derivative applied to the vector whose result will be the derivative. Will be 4, right? For this particular row here of this vector will correspond to psi j minus 1 minus the psi j corresponding to that line. It's this value divided by delta of x. So at any row of the vector, of the resulting vector, I will always have the difference of two values here in this vector, and is also divided by delta of x. So if I pick corresponding to this row here, I'll have a psi j plus 1, psi j plus 2 minus psi j plus 1 divided by delta of x. So as a matter of fact, I know that all the values in this matrix must be divided by delta of x. All right, all the values inside this matrix must be divided by delta of x. So this procedure is what I would have to do if I want to implement a numerical calculation of derivative. If you want to compute the derivative of a function in a computer, numerically, you need to write a matrix like this one. So Notice for finding this specific row here, I must have in some place here, all right, which corresponds to a complete row multiplying a column vector which corresponds to that row. So this is the j row here, the j row indexed by j, zeros, except where? At the position of j. So in the diagonal of the matrix, the jj component will be a -1. Why is -1? Because -1 zeros 0 times psi1 plus 0 times psi2 plus 0 times psi3 and all that. And when you stay in the multiplication of matrices here, when you arrive at this component of the vector, you must multiply it by -1 because the result is minus psi j. All right. So in the jj component of this matrix, you must have a -1. And now I follow the multiplication, zeros for j plus 2, j plus 3. So multiplying j plus 1, I must have a 1 here. Sorry, this is plus 1 minus psi j. So j plus 1 here, I need to multiply it by 1. So I have 1 here. And this is a diagonal matrix of the form of minus ones, ones, minus ones, ones, minus ones, ones, and zeros otherwise. So this matrix produces a vector which is the derivative function. So I can say always that a derivative operator, a first order derivative operator, corresponds to this matrix. 1 over the limit when delta of x goes to 0. In computers, you don't need to go to delta x goes to 0. Just pick a small value with respect to what you want to discretize, all right? So you find out a delta of x. This is an operator equation, and you'll find that -1 in diagonal, -1s, and 1s just after the diagonal, and zeros otherwise. This corresponds to the differential operator in matrix form. All right? So if you apply this matrix to a state psi and project onto the coordinate basis, which can be momentum if you are differentiating with respect to momentum, or any variable. Say I'm saying here position, but just it can be time or it can be anything. All right? And you project this thing, you'll find just the component, which is this thing here. All right. So this is the matrix representation of the derivative. It's an operator, it's a matrix operator. So differential operators are matrices in some limit where delta of x goes to 0. But when you go to the limit, you insert more and more -1s here, more and more ones here, and more zeros, and this becomes very dense matrix which has infinite number of values. It becomes infinite dimensional, so it's limit. It's a limit process. But if I remove the limit at first, I can produce a matrix representation of that operator. So I'll let you in the end with an exercise. So exercise here show that the second order derivative operator with respect to some variable, say call it x, is equal to the following. the limit when delta of x goes to 0, all right? 1 over delta of x squared, because it's a second derivative, so it must have the infinitesimal squared, all right? And this is the form of the matrix. Minus 2, 1, zeros. If you go to the limit delta of x going to 0, the matrix becomes larger and larger, all right? But in some finite value for delta of x, you can numerically compute that. You can implement this operator in the computer. This is the form. It has zeros outside this three diagonal structure, where in the diagonal you have minus 2, the value of the diagonal is minus 2, and one here, one position of the diagonal here goes to 1, so in the upper three diagonal values you have a plus 1, and the lower diagonal plus 1 also. So this is the second order derivative. It's important in calculating Hamiltonians, in evaluating numerical calculations for quantum mechanics, but it's just second order in one variable. You can find out for multiple variables, but in computers you can perform some tensor products like the Kronecker product, and you can use a single variable representation and perform some smart movements to find out what is the Laplacian. The Laplacian is also a matrix, and any differential operator is a matrix, as a matter of fact, in the limit where this thing goes to 0. So d2 dx2 is a matrix operator in the limit, operating on a vector in Hilbert space. In our case, in quantum mechanics, it's a Hilbert space, and this thing becomes more and more dense. It's become infinite dimensional in the limit of delta of x going to 0. And if you project onto the basis, you'll find out as a result, you'll find out the second order derivative of the components of the function with respect to x. All right, this is second order derivative. If you project onto the position basis, in the case where I am assuming x is position, but it could be time or momentum or frequency or whatever you want. So I am telling you that derivatives are, or differential operators are, represented by matrices. All right, and you can implement it in a computer. You can test it. You can make your own algorithm to calculate first, second, and nth order of derivatives. But in quantum mechanics, in many problems, just the first order derivative and second order derivative operators are relevant. And this way I am showing you just these two cases. All right, so a Hamiltonian, for instance, a Hamiltonian of this form, suppose a harmonic oscillator. It has a Hamiltonian of this form: momentum squared divided by twice the mass plus m mass, the natural frequency squared, x squared. These are replaced by a momentum operator, which is in one dimension, one space dimension. I'll call 1D problem. This is just minus I h bar, the derivative with respect to the variable x, and the Hamiltonian, therefore, can be represented by a matrix whose eigenvalues are the eigenenergies of the problem, And you can solve it by matrix formulations, or you can solve it by differential calculus also. But in the case of matrix manipulations, you need to be careful in order to take the limit. It can be painful sometimes, but you'll have minus h bar squared divided by twice the mass. This operator, which I showed you what is the matrix representation. So this is a matrix plus m omega 0 squared, the axis squared. So this is represented in the position basis. So this is non-diagonal. This is diagonal. You have only x squared over the diagonal of the matrix. All right. So that's it. You can use this to compute numerically. You can, if you know how to implement an algorithm, it's easy because you implement this matrix here, and this matrix is of the form in the basis of position is just the x1 squared, the x2 squared, the x3 squared, and zeros otherwise because it's diagonal in that basis. All right, it's diagonal in that basis, and now you can compute the harmonic oscillator eigenvalues. But you must be wise because this operator is symmetric when you change x by minus x. Also, the second order derivative, it's an even operator. So you need always to, in a numerical simulation in a computer, you need to pick symmetric limits. So choose from minus some value of x final till you reach the x final, you put endpoints. So your x1 here is a negative value, your x2 is a negative value, and then somewhere you find x equals to 0, then becomes positive until your final xn squared is equal to x1 squared, because this is a parabola, all right? So you need to have symmetric limits. Um, as a tip for you to calculate the matrix form of the second order derivative, remember that this derivative with respect to x of a function in the second order is just the limit delta f of x going to 0 of the derivative of the function evaluated at some point, say plus delta of x. Let us symmetrize that, divided by 2, say, minus the derivative of the function evaluated at a step earlier. It's in symmetric form. You can also represent first order derivatives in a symmetric form. There's no problem in that. But in computers, remember, if you define a delta of x over 2 does not exist. When you are in abstract language, you can always go to the limit, and that's perfectly fine. But in computers, you need to know what points are represented in your computational domain. So this is divided by delta x. So you see that here comes 1 over delta x squared, delta x. So that's why in the limit you can show that you will have this kind of thing here. Delta of x squared, psi of x plus delta x minus twice the function evaluated at the point x plus the function evaluated in 1 delta x previous to the point of interest. So you can also find generalizations for n order derivatives. All right, you will find it's very interesting to find out. So if you are interested in finding more general situations, try to find out what is this thing, right? What is this representation? So third order derivative is 1 over delta x, the second derivative minus the second derivative evaluated at neighboring points. And the fourth order derivative is the third order derivative at some point minus the third order derivative at some neighboring point divided by delta x. And in order n, you always find the divided by delta of x elevated to some n. But here you'll find a polynomial. This polynomial has some form, all right? And that's it. You can calculate. It's important for us, it's important to know how to calculate numerically the first order operators, the second order operators, and to know that differential operators are some limit, some kind of limit of a matrix. And that's why I said, that's why I guess Schrödinger also realized that the matrix mechanics and his undulatory form of mechanics was somehow related, because differential operators you can represent by matrices. So differential operators, the conclusion is that is this differential operators are proper limits when some variable goes to zero, some infinitesimal. You need to have some infinitesimal. They are proper limits. Delta x going to zero from applied to some matrix. All right. So that's it. Right. Hope you find it useful for some calculations, and see you next time.